Okay, so section 2.6 is limits at infinity, horizontal asymptotes. We already did this first one in class, so I'm going to go ahead and skip that one. I'm going to point out this fact right here. The limit as x approaches infinity, and that could be negative infinity as well, of 1 over x to the r, provided r is positive. If r is negative, then that gives you a reciprocal, which will invalidate this, is 0. And that's happening because if this gets big, 1 over big goes closer and closer to 0. As an extension of this, anytime the degree of the denominator is greater than the degree of the numerator, that is a proper fraction, the limit will be 0. Hence, the function will have a horizontal asymptote y equals 0. One technique for finding limits at infinity of rational functions is to divide each term by x to the n, where n is the largest degree of all the terms. So when we look at this first example, x squared, that's our highest degree term. So that means we're going to divide everything by x squared, and we get the limit as x approaches infinity of 5x over x squared plus 1 over x squared over x squared minus 5 over x squared. And if we reduce these fractions, we get the limit as x approaches infinity of 5 over x plus 1 over x squared over 1 minus 5 over x squared. And if you look at all of these, 5 over x goes to 0, 1 over x squared goes to 0, 5 over x squared goes to 0. And so what we get is 0 over 1, which is 0. Note 0 over 0 is indeterminate. Which is not the same as d doesn't exist. It means indeterminate, meaning you cannot determine whether the limit exists nor what it is when you get 0 over 0. But 0 over a constant is in fact 0, so this limit actually is 0. The second one, if we do something similar, the highest degree is x to the 4th. And so if we divide each term by x to the 4th, by the way, we're allowed to do that because we're basically multiplying the numerator and denominator by the same thing. So we're really just multiplying by 1. So what we get is the limit as x approaches infinity, dividing everything by x to the 4th, we're going to get 9 plus 1 over x cubed over 2 plus 5 over x squared minus 1 over x cubed plus 6 over x to the 4th. All these things with the denominator growing to infinity go to 0. And what we get is 9/2, which, if you remember from pre-calculus, is the ratio of the leading coefficients, which would also be the horizontal asymptote if we were to graph this function. So this graph has a horizontal asymptote of y equals 9/2. This last problem is not a rational function because of the square root, but we can still do something similar. Remember, what we can do here is put this whole thing under a square root so that we've got the limit as x approaches infinity of the square root. So you see what we did here? We just squared this so that we could put it underneath the square root, and it's still the same thing. Now we're using that property that limits have, where you can compose the limit of a composed function would be like this. So we can pull the square root out as long as it's continuous. The square root is a continuous function, so we can do that. And then look at this. I'm going to expand the x minus 1 squared. So x squared minus 2x plus 1. Now if we take the limit inside the square root, I'm going to shortcut it a little bit because we know that it's going to be the ratio of the coefficients when the degrees are equal. And so what we get is the square root of 3 as our limit. So horizontal asymptotes occur when you take the limit as x approaches infinity of the function, okay, or negative infinity. If you remember, just kind of a review, if we have a function that is a ratio, usually we're talking about polynomial functions when we're talking about this. When we're talking about horizontal asymptotes in general, not that other functions don't have them, but these are the ones that we're usually dealing with, then we're going to look at the degree. If the degree of the numerator, p, is greater than the degree of the denominator, q, that's an improper fraction. And there is no horizontal asymptote because the limit as x approaches infinity of f of x would be infinity. If the degrees of the numerator and the denominator are equal, then y equals the ratio of leading coefficients. And lastly, if the degree of the numerator is smaller than the degree of the denominator, then you have a proper fraction. And your horizontal asymptote is y equals 0. So this next example, we want to sketch a function with all these qualities, all these properties. So let's start by drawing our axes. And then let's start with what this first thing tells us. So the limit as x approaches infinity of f of x is 3. That tells us that we're going to have a horizontal asymptote, y equals 3. I'm going to go ahead, I'll put that in a second. And put the scales here in. Okay, so let's go ahead and put in the horizontal asymptote. We know that that's there. The next thing that we're looking at is these next two limits. One is from the left, one is from the right. And one is positive infinity, one is negative infinity. So what that tells us, what these two tell us, is that we have vertical asymptotes at x equals 2. So what's going on here, if we're just looking at the x-axis, and here's x being 2, if the limit is coming from the negative direction, then we're going to positive infinity. So that means that we're approaching positive infinity on this side. And if we're approaching from the positive x direction, then we're approaching this asymptote, or the y values are approaching negative infinity on that asymptote. So I don't want to draw that in the graph just yet because I want to make sure that we satisfy this last stipulation. That's that f is odd. F is odd just means that it's symmetric about the origin. So with just that information and looking at this graph, I'm going to go ahead and look at the values of x greater than 2, and I'm going to go ahead and just put this here. A graph that did this would satisfy all those conditions. And so the other half of this graph is going to have to follow its asymptotes too, and it's going to have to be symmetric about the origin, which is going to be something that looks kind of like this. So that this curve here is a mirror of that across the origin. And that's pretty much all we can do for that one. For number 4, we want to sketch the graph of f of x. So the things that we want to find are the zeros and vertical asymptotes and horizontal asymptotes. So when we find the zeros, that's where f of x equals 0. And so that's where 2x squared plus 1 would equal 0. 2x squared would have to be negative 1. That gives us no solution, so there are no zeros, which means that the graph doesn't cross the x-axis. Vertical asymptotes, we look at the denominator. So for the denominator of f of x, I'm going to factor it. We've got 3x and x. To get 3x squared, we're going to have 1 and 1. This will need to be negative and this positive in order to get the positive 2x. So if we set the denominator equal to 0, then x equals 1/3 and x equals negative 1 are my vertical asymptotes. And then for the horizontal asymptote, we just want to look at the limit as x approaches infinity of our function. And you can see that the degrees are equal. So we're going to get the ratio of the leading coefficients. So the horizontal asymptote is y equals 2/3. Let's go ahead and see what we can get out of that for our graph. So here's our axes. My numbers are small, so I'm going to scale accordingly. So no zeros. We have to remember that that means we don't cross the x-axis when we're actually putting down our graph. Vertical asymptotes, x equals positive 1/3. That's about here. And then x equals negative 1 is here. And then our horizontal asymptote at 2/3 is about here. And now we just need to figure out where things go. Our asymptotes will guide us quite a bit because they will tell it our graph has to approach the asymptotes. Okay, so let's go ahead and take a look really quickly here at the signs. and by sign I mean plus or minus, of f of x. I'm going to kind of copy over the x-axis, and the points that I'm interested in here, the points where the signs are able to change, are anytime any of the factors of the original function are 0. So that numerator can't be 0, but those two denominators can be 0 at -1 and at 1/3. So this is where those are the points, the x values, for which our graph can change from positive to negative and negative to positive. So our function, let me go ahead and rewrite this. The 2x squared plus 1 is always positive, so I'm not even going to worry about that one. And then 3x minus 1 times x plus 1. We can look at those factors because those will vary. So in this interval here, this x plus 1 is negative, and this 3x minus 1 is positive. And so overall, we get a negative y value for all the x values less than -1. And if we look at our graph, is that possible? I think I'm positive. This is negative, positive. That's not possible, so I need to reevaluate. The reason it's not possible is because if our graph is negative in this region, that means it's down here. And we can't cross the x-axis, and so therefore we can't approach this asymptote either. So I'm going to pause it here, and then we'll go over it in class just because I want to make sure that this video gets posted. But we'll go ahead and finish this in class. No big deal. Let me just undo these things real quick, and we'll reevaluate that in a little bit. Just have one more problem here, so let's go ahead and do that one. Now, this actually has a typo, which I went in to fix and then forgot, and now I'm too committed to this video to start. But this should be the limit as x approaches -infinity of the square root of x squared plus 3 plus x. If you mentally substitute in the -infinity, the infinity squared, -infinity squared will be positive infinity, so this first expression will be infinity, and then this is minus infinity, and this is an indeterminate form. So we don't know if the limit exists or if it doesn't exist or what it is, anything like that at this point. But we do have something that we can do to algebraically manipulate this, and that is to multiply by the conjugate, x squared plus 3 minus x over square root of x squared plus 3 minus x. So by doing that, we will algebraically manipulate this thing and then hopefully be able to take the limit. So the limit as x approaches -infinity. The numerator, when we multiply those conjugates together, we're going to get the square of the first minus the square of the second term. And then in the denominator, we just have 1 times the conjugate. So we're going to get square root of x squared plus 3 minus x. And that's it. So now what's going to happen is that our x squared minus x squared add to 0. And then what we end up getting is just the 3 over the -infinity squared here plus 3 is going to be infinity. And then this here is minus a -infinity, which gives us infinity plus infinity, which is infinity. Okay. And so that's the limit. The limit as x approaches -infinity of this function is actually, whoops, not infinity. Just kidding. The denominator is infinity, which means 0.